It's now my great honor to introduce our keynote speaker for tonight, Professor Alastair Guthrie. Welcome to EPFL, Alistair, for this lecture and the opening of the exhibition Solar Decathlon. Alastair Guthrie will share with us his profound experience in sustainable design and construction. In this domain, he develops an exceptional expertise as Professor of Environmental Design in the School of Built Environment at Nottingham University in the UK, and as a visiting lecturer at the Royal College of Art. But also during his practice as leader of Global Building Sustainability Network for the ARUP Group, one of the larger and most amazing engineering firms. Maybe I should start to say a few words on ARUP, although all of us probably know it. If an architect has an exceptional and difficult design in mind, he or she probably will call ARUP. The list of great architects who partnered with this company is impressive, starting with Jorn Utzon for the Sydney Opera House, including Rem Koolhaas, Norman Foster, Herzog & de Meuron, Alvaro Siza, Renzo Piano. This firm has seemingly become the go-to office for the most structurally and logistically complex projects of our time. It was founded by the philosopher and engineer Etfe File in 1946. Etfe File was both a humanist and a builder. He inspired the company with strong principles like extensive, collaborative, and cross-disciplinary work, a high degree of independence and responsibility given to ARUP members, and a high social awareness. Tristan Carfrey, a colleague of Alistair, stated that ARUP is a sort of club where everybody is working for everybody else at ARUP. The result is that people learn from each other and generously share their knowledge and ideas at the very horizontal level. This club counts now no less than 12,000 members all over the world, providing engineering, design, planning, and consulting services for all aspects of the built environment. Although at a very different scale, we thought that this holistic approach and this excellent work ethic should inspire a project like the Solar Decathlon. Alastair Guthrie joined the company in 1972 after studying building engineering and acoustics. He is leader of Global Building Sustainability Network and ARUP Fellow. ARUP Fellow is an honorary title awarded to very few individuals in the firm. It acknowledges the highest design and technical achievements of an ARUP person, not only within the firm, but also in the industry as a whole. They are considered role models with world-class expertise who put theory into effective practice, and I here cite Wikipedia. Alastair Guthrie's expertise is the application of building physics and microclimate design to find sustainable solutions to the built environment. He has participated to the construction of, for instance, the Seattle Public Library and the CCTV in Beijing by OMA, and for not less than 13 projects with Renzo Piano, including the Menil collection in Houston, the California Academy of Science, and the London Bridge Tower, the Shard. Alistair is convinced that the best design solutions are both integrated and sustainable, as he will probably tell us in better terms. It goes without saying that we do share his view at the ENAC School and at the EPFL at large. Your work, Professor Guthrie, will be an inspiration for the students who are currently researching for the Solar Decathlon Challenge, but also for our school at large. Thank you very much for being with us tonight, and the floor is yours.
Okay, can you hear me all right? Yeah, good. Okay, well, what I want to talk a little bit about tonight is this topic, responsible design. And what I'm going to do is to describe a little bit about the origins of ARUP, which you've heard the beginnings of, because I think that explains something about where I'm coming from as well. I'm going to talk to you a little bit about what I mean by responsible design, and then I'm going to show you some projects where I think we have begun to achieve some of these goals. Nothing is perfect, I will say. It could always be better. So, let me talk first of all about This is a picture of ARUP. He, as we've heard, studied both philosophy and engineering in Denmark. Although he was born in the UK, his parents were Danish. So the firm he founded, ARUP and Partners, was founded in England and has since then spread throughout the world. So the basis of the firm is an intellectual independence and a shared value derived from the beliefs and convictions of ARUP. And in 1970, he produced a document which has been called ever since the Key Speech. This is available on the internet if you want to read it. And it was a treatise that was put together by ARUP about how he saw the firm, if you like, continuing as it grew. And it's a slightly philosophical, it's a chatty document. It's a document that was written to the partners in the firm, but of course is relevant to us. And every so often people get it out, dust it off, read it and say, is this still relevant to us today? Is this still something that is worth reading? And genuinely and always people come back and say, yes, it is. There's a few sort of words that don't fit very well with today's culture, but beyond that, it's a pretty good document. So from that beginning, the firm has expanded to 90 offices in 35 countries, and we have about 12,000 people employed, not just engineers, but obviously the largest number of people are engineers. That's where the firm started. And what we want to do is to deliver innovative designs with our collaborators across the world, and we like to think that we can do this with creativity, imagination, and passion. And those are the things that kind of mark out the firm. It's why I have been in the firm for 36 years, and it's a difficult place to leave because you can achieve a lot there. So this is just a picture of where our office have grown, the first office in the UK, and from there. I think, you know, the office in Sydney for the Sydney Opera House has been there ever since. That was almost the second office, so it shows you that the reach has changed. So, as we heard before, firm was founded in 1946 with these set of values that were set out in the Key Speech later, but and a very interesting corporate structure, which I think is partly the longevity of the firm. The firm is a charitable trust, and therefore there are no partners that are equity partners. The profits or the part of the firm is divided by amongst all the employees. And so as such, the firm can continue through one generation of leaders and directors or partners to another without having to buy and sell. So, and that happened in, I think it was about 1970, it was set up like that. But the basis of the work that we do is about integrated collaborative working, sitting together, working together. Each person's contribution is valid and is as important as somebody else, and that together we believe that that we can get a better whole by joining with all the members of the design team. So this idea of integrated collaborative working is reflected in everything we do and helps us to shape agendas and deliver results that we hope surpass the expectations of our clients and our collaborators. But this idea of approaching a project in an integrated way, and the idea that nothing should be approached in as an isolated idea. I think he used the word "no man is an island" within the key speech, and he coined this term "total design," and that's about collaboration. It's about everybody having a unique part to play in the resulting project. But this is another idea that came from him, because he was obviously basically a philosopher. He called this the guiding star principle, and the idea was that we put out something in front of us which is the best possible, the quality, the best possible solution to a project, and then we use that in front of us as our guiding star, the way that we go, our direction. We don't always get there in a straight line, but that's our aim. And this principle was something that I use when I develop a strategy for sustainability for ARUP, about 7 or 8 years ago, where we said, what do we really want to achieve? You know, what do we put out there in front of us? And we came up to a number of what we call objectives. We had 6 of them, things like carbon neutral, water sufficiency, and we used this guiding star principles to put them up in front of us to see how we could approach them and get close to them. So this is our commitment to sustainability, is to put sustainability at the heart of all our projects, and seek to make a positive influence on the world in which we live. And it's quite interesting that that although the word sustainability was not something that ARUP would have used, because it was kind of not the buzzword then, but he did talk about many things which we today would call sustainable design. So let's just I'll come on and talk about this project. It's the California Academy of Sciences. So another thing that as ARUP we do, and I want to talk a bit about this, is that we invest in research and development, because unless we put investment into innovation, and we innovate continuously through research projects, but also through our own projects. You know, you do it on the job and off the job, as you know, together. Then we will not be able to bring new solutions, new ideas, new directions to our projects, and of course, you know, as we know. Very appropriate today with COP21 started, the climate change is a huge challenge which demands that sort of level of innovation and integration if we are to solve it. So ARUP is the creative force, as we heard, behind many of the world's most prominent projects. I hate to use the word iconic, but we do. And I want to talk to you about one or two of those this evening. But first of all, I just want to put this quote up, which is a kind of preface to everything that I want to say. as a quote from Sir of ARUP, a design team which produces a totaled, balanced, efficient design can help produce a better environment. This is a statement about sustainability without using the word. And this is about integration, getting together, cooperation, getting efficiency out of our design, and therefore creating a better environment, more sustainable solutions. Of course, the definition, which I'm sure will be mentioned at COP21, which is, I'm sure most of you have seen this definition, but this is definition of sustainability, which is slightly more broad-ranging, more broader functioning than of ARUP, his statement. This is from Brundtland. It's meeting the needs of the present while not compromising the ability of the future to meet its own needs. And that's what I mean by responsible design. So that what we do today is good for today, but also is good for tomorrow. So what impact does the buildings and that we design have on the world in which we live? Let me give you some very quick flash statistics. These may not be 100% up to date, but they give us the direction that we are thinking in. So construction itself, building stuff, is actually very good for work because it employs 10% of the world's workforce. It's the largest employee of micro firms, which employ less than 10 people, and contributes a very varying amount of national GDP depending on which country you're in. But so construction is good. And people say to me, well, you know, I just like the green fields. I don't want to touch anything. So let's imagine that a sustainable future involves construction. It's good for us in different ways. It's good for us because it can have a big impact on the quality of our life. The beauty, the elegance of our cities that we walk through are largely framed and function by the buildings which sit within them and the spaces that they create between them. And our buildings, our construction is able to improve the society in which we live through hospitals, health, education, by creating better social fabrics, by creating cities which are nice to dwell in. So construction can and does enhance society. But of course it needs to be efficient because it consumes around 30% of the world's resources. It sends, or I think this is an old figure here, it sends 40% of its waste to landfill and consumes 12% of the world's water. So what we build, as we build it, has a huge impact on the world in which we live, okay? Of course, our cities and the energy that they consume has a huge effect on the greenhouse gas. And that's why at COP21 they are finally having some sessions on the effects of buildings, which is really important. And our construction, it's important that we think about preserving the balance in the ecosystems which of the world. And I don't mean just a green roof like this one. I mean the materials that we use, the extraction, the one-way use, the consumptive extraction of materials. And the building industry is very uses a lot of that, and we need to think about that in how we design. So this is where I think we want to go. Okay, so what I think is that we need to think about what is our responsibility. What is responsible design? We can put in intuition and research, and I'm going to talk a bit about that. And hopefully the outcomes that we're looking to get are efficiency, and elegance within our built environment. And that's a kind of pattern which I hope I can illustrate a bit of. So, intuition and research. This is a quote from Paul Clay. I think I'm in the right place to use this quote. So he said, where intuition is joined to precise research, it speeds the process of precise research. There is no substitute for intuition. And why I think that is important, I think that setting off in the right direction on a project is fundamentally important. So our intuition about how we put something together, the ideas that we have at the beginning of a project, we can support those, we can research into them, and I'll give you some examples, but we have to get that direction right in the first place. And that, in a way, is the most difficult thing. So this is the first project I want to talk about. This is the Menil collection in Houston in Texas. It's about 30 years old now. Well, it was 30 years since I started working on it. I think it's not quite as old as that. And this was a museum. The architect is Renzo Piano. And the thing that was really important was this idea that he had, and that hopefully we supported, was this idea of what he called the platform roof. So this thing here, this platform roof joins the galleries at the bottom to the storehouse at the top. And this platform roof, the idea was that it was an integrated element of the building. It did everything, or mostly everything, of what the building needed to do in this one element. So that was the concept. So this is it in section. I'm sorry, this is a very bad slide, but this is, like it's sort of 30-something years old. So and I found it in the archive. This just shows this platform roof, shows the storehouse at the top and the galleries underneath. But one of the other objectives that even at this time, people were interested in energy performance. So right at the beginning of this project, we said, what's the difference between having a black box with artificial light for the galleries and a top-lit gallery with daylight? And of course, there's some pros and cons of both of those, energy-wise. And actually, in those days, it was actually slightly more efficient, very slightly more efficient, to have a black box and artificially light it. But of course, so that was the pure energy argument. But of course, the argument to have a day-lit space that was beautifully lit, that you could appreciate the art, was of course overpowering. So it was only about 15% difference. So it's just to say that it's a quite different equation, and I'll illustrate that in some other things. But about collaborative research, this is me. As a few years ago, and that's whoops, let me see. That's Renzo Piano. That's Peter Rice, if people may know Peter Rice. So this was all about together, and this was the workshop, which happened to be in Renzo's garden, where we sat down and worked out the shape of those leaves that I'll talk about a bit more, the ideas that came out of working together. So this is about collaboration. And these shapes were what we were planning and drawing on the ground there, was the idea, how could we get something that was a structural form, that reflected light into the space, that kept the sun out of the space, that provided a platform for all the high-level services, that provided a device to do all the artificial lighting from. So this one piece was constructed in such a way to do all those functions, and that was what we meant by integrated design. And we did lots and lots of tests. So that was the idea, that was the intuition, then of course this is the research. So this was about making a model, looking at light, the light reflecting properties of the thing, measuring it in a model, and then actually building a full-scale mock-up, which is here on the left. That's me again. And that is the real project on the right. So this mock-up was testing the ideas, testing the shape, looking at the colour, all the issues to do with what that shape was made of. In the end, we made it out of ferro cement. I'm not going to go into all that part of it. That was more the structural area, and a type of cast iron. And so that element did everything. You can see here the lights that hung from that element as well. There was air conditioning ductwork in the ceiling. There was all sorts of things that actually are supported by that one shape. And the final gallery, you can see the shape from the inside. See the way it reflects the light into the space while blocking out all the direct light, and that span is also, that element is also the structure. It's not an added piece, it is a piece of structure as well. And here it is on the outside of the building with the glazing above it. So that's an example of integrated working, all the disciplines coming together to get a single solution that works for the project. This is another more up to date. This is in the City of London. It's a building that was built probably 20 years ago now, I think. It's called the Helicon, and the issue here was how to do something. We were just coming out of the recession, and the client said, we want to do something which positions our new building, he was a developer, in the marketplace such that we can be a differentiator when the market comes back on stream. So he was really keen to make this project a low energy project. And so we had a look at all sorts of issues, but the basic idea was to make the building as transparent as possible, so that we could make the most of the daylight within the space, and yet conserve both the heat and keep out the sun from the building. So those were that was the goal, and this is the picture of the skin, and this is one of the early double skins. This is single skin on the outside, double skin on the inside, and we came up with this idea of active blinds. Now, the point of that was that the big surfaces in this building face east and west, so most of the glass was either on the east or the west. So at least half of the day, there was no sun on one side of the building. In London, of course, we get lots of grey days, so it was a lot more than half of the days where there was no sun. So the whole point was, let's be able to take away the blinds when we don't need them, go for as much glass as we can, get as much daylight into the building, and but when the sun is shining on the building, these elements drop down. They fold up at the top, they drop down, and then they tilt to the right angle. So this was one of the early active double facades, and what that did, of course, was to reduce the solar gain right down, such that we could use a different type of This is a different type of air conditioning system. This is the retracted blinds, which you can see at the top there, and the full glazing. So as well as this this system in here, we also did the first system in the UK, I think probably used earlier here in Switzerland, I have to say, of underfloor air supply and chilled ceilings, both of which were innovative, but which we could only use because we had reduced the cooling load enormously on the building. So this is just it's a very early CFD. It looks terrible now, doesn't it? It's funny how these things change so quickly in 20 years. This sort of looks like really old-fashioned. And here's the chilled ceiling. They didn't actually exist as a panel in those days, so we made our own. We knew what we wanted it to do, so we just bought some ceiling panels, standard metal ceiling panels, put a coil behind them, and it became a chilled ceiling. So this was an idea of trying to do something and then thinking very much in a different way. So the first speculative building in London to have this sort of facade, and the first speculative building in London to have a chilled ceiling as well. So ideas, doing a bit of research, trying to make the thing work, and then building it. So this is probably the biggest project I've ever worked on. It's the longest project. It's Quinze Airport, and I'm not going to talk about much. I'm just going to talk about one thing on this airport. There's the terminal building. It's from here down to there. It's 1.8 kilometers long, and it has across here, from here to here. This is the departures hall. From there to there is 80 meters. The concept and the idea at competition stage for this project was to have a shape which was like an aircraft wing, but which also enabled us to air condition the whole of this space, 80 meters, through a series of jets that were placed in this position here, like this. So again, some old drawings. So the jets are here, and they blow air across this space and create a circulation. So we have what we called the macro system and the micro system. This was the idea behind this project, and the idea was to be able to supply all the fresh air, filtered fresh air from these. We only had 17 of these jets across the whole length of the space, but at the same time to create an atmosphere which I called a gentle breeze. So the idea was that when you go into an airport, you go with your coat on. You're not going to take your coat off. You don't want it sort of, it's almost like an outside space, but it needs to be protected outside space, protected from noise, from pollution, from all sorts of things. So the idea was to use these jets to create an air movement. There was a gentle breeze, made people feel comfortable, and created an environment that was slightly different to other things. In order to do that, we had to imagine, we had to actually design this jet. I mean, you couldn't buy a jet that did this, so we designed it from first principles, built it, and tested it. We also used, again, computational fluid dynamics to work out the velocity of that jet, the mass of air we had to put in, all sorts of parameters for that air. And it seems, again, strange, but at that particular time, this was a huge model, a massive model, because of the size and the type of jets. And in ARUP, we did not have a computer big enough to run this model, so we had to go to a research university, buy some time from them so we could run this model. Of course, you can all do this on your desktops now, but that was the way it was then. And here's the jet. And in order to make the air travel at 80 meters, we made this fabric, what we called an open air duct. So the air stuck to this thing. It's a bit difficult to see from this picture, and that enabled it to travel a full 80 meters across without dropping. And there you can maybe see a little bit more closely there. Okay, so it's a project in the UK called the Eden Project. It's in Cornwall, which is in southwest England. And the client's ambition for this project was to build the biggest greenhouse in the world. And he wanted it as a tropical greenhouse. And our challenge was how we could do that with as little energy as possible. So that was the kind of framework which we went into this project with. There was a lot of discussion about the site in the early days, but in the end, the client bought an old quarry. This quarry was for china clay. They extract china clay. It's very soft, the ground. They extract it by using a high-pressure water jet, sucking it out. And it's the material that they use to make all the pills that you take, the white things. So that was what they extracted from this thing. But at the back of this thing, they extracted the soft rock, and there was quite hard granite. So the idea was to enclose the this edge of the cliff with this very large structure. And to build the tropical rainforest within this space. So the challenge was, how could we enclose it efficiently and yet allow as much sun as possible? It faced south. We wanted to get as much sun as possible, absorb it in the rock structure, and prevent it losing all that heat at night. So we needed the property for that enclosure was highly transparent, very lightweight, and highly insulated. That was what we were looking for. And basically, greenhouse glass is not those. It doesn't have any of those properties. So we had to look for something else. So came up with, and I'm sure you've all seen this now because it's used quite a lot, but it wasn't used very much then. This is Etfe Foil. It's a thin plastic membrane, and we used either 2 or 3 layers of this, and it sat in a frame here, and it was inflated using compressed air, so it became a bubble. And this material itself is highly transparent. The individual layers are about 95% transparent, and they are as good as double glazing in terms of the total thing. So, and of course it's very lightweight, and because the frames, the maximum pieces on the Eden project are 9 meters across, so very large pieces, very lightweight. Of course, lightweight was good for the structure, but it's also really good for the lighting, because the last thing that we wanted to do was to block out the light. So the idea was we could let as much light in as possible. So that was the material that was used. In order to take that idea and test whether we could do it, the other concept we had was we didn't want there to be any systems, any heating or anything, any ventilation within the whole area of this space, because they wanted to be free to plant as they wanted. So we used the same principles that we did on the previous project on Quinze Airport, and used high-powered jets to provide all of the heating and air movement to the space. And these are much less elegant jets in that case. But here's the material, and of course, keeping it warm is one thing, but stopping it getting hot in the summer is another thing. And so we be able to open the top and let the air out. And this was a very early picture of the space. And you can see this huge space, but very light, very transparent, able to collect as much heat as possible and store it in the rock at the back here. And just just to say that the other issue, of course, with a tropical thing is humidity. We had to create a humid space, and this is a picture of it, and we've done that by individual sprays, tiny high-pressure sprays that are in the space. The problem we had was that all the groundwater, let's remember it's a china clay pit, all the groundwater we could extract was white and full of solids of china clay, so we couldn't use those in the spray. So actually in the end we collected all the water off the roof of these biomes, pumped it to the top, used some existing tanks which we relined, and then it's fed down to these jets. I think you can just see one of those spray nozzles there, and that keeps the it doesn't look like this except early in the morning, unfortunately. Okay. How are we doing for time? Okay, good. Right, so I want to talk about another museum. Again, this one is with Renzo Piano again, and this is in Atlanta. And this museum is quite different. The Menil museum that we did, we were able to block out the direct sun by these linear, what we call leaves, because the museum is on a block that faced north and south. This museum is on a block that doesn't face any particular direction. It was 37 point something degrees from it. It was an odd facing block. So how do we get the same idea for the top light? So we explored all sorts of issues, these sort of horizontal ideas. But in the end, it came up with a series of circles set in a grid, which we could block out the direct sun, but allow the right amount of daylight into the space. This is just it's a illustration of the sort of collaboration. This is a wax model made from the piece, which we made in our offices. Renzo's office made this concrete piece, and we made a lot of other models on this thing to just experiment. There are some of these. Some of these are computer models. Some of them are made with wax, some polystyrene, some plaster. Anyway, the whole thing was about collaborations, integration, working together to produce some sort of ideas for the project. And again, this is a full-scale mock-up of the idea. And this is the project which used these circular things with these big cowls, and these cowls provided a screen from the sun. You can probably just see in this photograph that the sun is just here. You see that? The sun is shining on it here, but doesn't in any way touch the glass. So, and this is obviously, you have to plan this through every time of the year, every hour of the day, so this achieves this type of solution. Oops. Yeah, and these are these rather strange cowls on top of the roof, and a picture of the gallery inside. This one is in Texas. It's called the Nasher Collection. It's just across the way from the Museum of Modern Art in Dallas. if any of you have been to there. And this was a private collector who wanted to build a space, a garden and a pavilion, so that he could put his collection, give his collection to the city of Dallas. There's a guy called Ray Nasher. Again, this is a piano museum, and the concept here was strong stone walls with a very lightweight roof for the pavilions. The challenge that we came up with right at the very beginning, the idea, this was obviously the architect's idea, was that together we wanted this element, which is the roof, to be as light and thin as possible, and yet it had to do all of those functions that we talked about for the other roof. It had to exclude all the direct sun, because you can't have sunlight on objects of art underneath, so it had to exclude it all. It had to filter the light, had to provide a waterproof, had to have a very thin structure. So and we had to be able to hang the lights, the artificial lighting. Everything was done on that very thin roof. So the challenge was, how could we do that together? So we worked with all of the people in the design team to come up with a number of things. So the first of all was the sun excluding grid, and these are all types and different solutions to that. And I made a wax model of this one and this one, and I took it to the client, who's a collector of sculpture, just imagine, at Scheme Design, and I said to him, well, you have an option. This one works, this will cut all the sunlight out, so does this one. Which one do you want? So, and of course, this is cheap, this is expensive. But he decided that the shape, the importance of this thing was so crucial to what the museum looked like, that he said, let's develop this idea. So we worked on wax models, and then we cast those wax in aluminium. I think that might be an aluminium casting. Anyway, we cast them directly from the wax, and then we went to a foundry and they cast them better, and started to develop this shape. We did all the geometry, they did all the casting, because of course they could, our wax model used about 4 times as much aluminium as it was necessary, so they worked on that. And we came up with this shape here, which sits as a grid on top of that roof. The roof is curved steel members, which are hung a suspended midpoint, so they only so they're as thin as that, and the glass of the roof is underneath this structure, which you can see from here. This is the glass. These are the elements of the steel, and that also took all the lighting tracks. But you can see also the effect of this grid. This picture is looking to the north. So when you look to the north, it was kind of transparent, whereas when you look to the south, it was opaque. And that, of course, is what we're trying to achieve. So this lets the maximum amount of light in that comes from the north light, whereas it excludes all of the sunlight from the south, and not just the south, but tracks the sun all the way around. There's another picture of the shape from underneath. So this became something that is very much the signature of the museum, and yet is being derived from mathematical some paths and principles, but being made into a shape that gives the museum its character. And this is the picture from inside. And there's another museum that we've done subsequently to that one, which is just down the road. This is in Fort Worth. it's not this museum, because some of you may well recognise this museum. This is obviously Louis Kahn's museum at Fort Worth, and of course this is another Renzo Piano project. Of course, when they came to him and said, would you build an extension to this museum, I think Renzo was rather thrown, because of course Louis Kahn was one of his sort of mentors, and you know, to build next to it was difficult. So in the end, the idea was to build we looked at a site that was in fact across the way. So this is the new pavilion, and this is the old Louis Kahn pavilion. So to get from the original site they gave was somewhere down here, but in the end this was something that could be opposite, could be important to reflect the original Louis Kahn building, but still be completely separate from it. So again, the challenge here, coming back to that very early thing that I talked about on Menil, we did a study here to say, if you have a black box, a gallery, you use a lot of electric light but very little air conditioning, because you haven't got daylight. If you do this the other way around, you use a lot of air conditioning, but this is 100% glass, but you don't use much lighting. So we determined there was a point here which was optimum. And so how could we design within that? So that became one of the things that we tried to do. But unlike the other museums, used the same principle, this linear principle, because of the way it was orientated, north-south. But here we said, I said to the client at the very first meeting and with Renzo, would you be interested in thinking about how to make this gallery carbon neutral? Can we make it so that it generates as much as it uses over the course of a year? And so he said, well, yeah, sounds like a great idea. So hence the challenge. So we kind of set ourselves up for a challenge, really. This is what we ended up with, was a series of louvers which controlled the light, which kept out the direct light. Again, same principle as we used on the other museums. But these could turn. They're two positions, so you have a summer and a winter position, so better angle for the light, better angle for the solar. They all have on them, as you can see, PV cells. And we had to solve quite a lot of challenges for this. The main one being that in Fort Worth, they have hail the size of tennis balls or cricket balls or whatever you want to call. And they're very worried about the fact that these would break the PV. So these PV, I think, which picture it is, anyway, they turn over. You can turn them over. They've got a motor on them. So if it's going to hail, you just turn them and they flip over, and the backside is then pointing upwards. So it sounds like an obvious solution, but it took us a little bit of time to come up with that idea, and also the mechanisms to really make that work effectively. Having sort of generated the power that we could from the gallery, having dealt with all sorts of issues like the facade and the wall, we also designed systems that would use the minimum amount of energy, ground source, cooling and heating, various types of advanced heat exchangers. So we didn't achieve exactly what we wanted. This is the existing Kimball Museum. This is our museum with no photovoltaics, and this is where we got with a photovoltaics. And so we didn't get to a completely carbon neutral gallery, partly because they kept adding lots of different functions like auditoriums and things, not just a gallery. It made it more difficult. But we got a long way by using that idea of the guiding star. Let's start with aiming for something very high and then see how far we can get. and this is a picture of the museum. And this is the entrance which faces the Kimball on the other side. California of Academy of Science. I think this, for me, I'll explain the project a little bit, but for me there's one fundamental thing about this project which is why I like it. This was almost the first sketch we drew of the project. It showed the ambition of the project, the ideas of the project. And I look back at this sketch, and then when I went to see it after it had opened, and I thought, you know, we almost completely managed to keep all those ideas and build them in. And that, I think, is very unusual. Actually, it's pretty rare to do that. But it shows you if you start in the right direction and you have the right ambitions and the right imagination, you can begin to move towards achieving some of these things that you imagined. So one of the big concepts of this space was the very large open area of the exhibition hall, which is all this with these big spaces that sit in it. The idea was to have a roof which sat over all of that and had these mountains in it, these bumps, and they were there because of this concept, which, if you imagine the wind that blows off the Pacific Ocean, comes through Golden Gate Park. It comes to one of these domes on top of the thing. It gets compressed, and then it causes a negative pressure here, and that pulls the air through the slots at the side of the underside of the hall, through the hall and out through the top. This is a really old principle. This is nothing new at all. It was used in Iran, I don't know how long ago, but a very long time ago with the way that they used the desert airflow. So this was the principle, and so these are the domes, and these are the holes on top of them. You can see them like this, so they open up, allow this negative pressure to pull the air through, and they were also used as daylight devices. And coupled with that airflow through is that all of the ceiling and the walls and the floor of that exhibition hall are made from concrete, so they act as a heat sink during the day, and then they're cooled down at night. And at the same time created a garden on that roof and added photovoltaics to provide at least some of the power for the museum. And this is the latest project. It's only just opened. It's in Malta, and it's a new city gate, and this is quite a different concept altogether. Malta is one big rock. Okay, the whole of the island of Malta is rock. It's made out of this sandstone, and so the idea was the building was made out of this rock, as are all the other buildings in Malta, but that we would carve it in such a way to achieve a very efficient facade with that would keep out the sun. So you can see this is a carved facade keeping out the sun by the angles of these fins. And here's another shot of the final building from the outside, these fins. From the inside you can still see out through the windows, but they're partially shaded by these stone fins. The stone is inside and out, so it provides a heat sink in the building, both from the heat coming in and also going out, and all the windows are opening because in Malta, being an island, there's quite a good breeze that comes across particularly in the afternoon. So we want to maximise that. So heavy stone, shaded facade, and natural ventilation. So that was the basis of the project. And to that we added, we decided that we wanted not only to use the stone in the building, but we wanted to use the stone underneath the building. So we put these heat exchangers down 150 metres into the rock underneath that provide storage for excess heat in the summer, and we can pump that heat out during the winter and use it to heat the building. This is the principle of that. So it provides all of the heating and most of the cooling. There's this little bit of extra cooling we need to provide. And as a result of that really driving down the energy performance, this solar small photovoltaic array on the top of one of the buildings can provide about 60% of the energy needed for the building, because we've reduced it to such a small amount that this then becomes a major contribution. And of course in Malta, one of the other areas is water. There is no water on the island apart from what they collect. And traditionally they've collected rainwater underneath every house in Malta. They have cisterns, and so that we've done the same. We've collected the water. In fact, we found a cistern under the building when we excavated, so we used that, collect the water, and that is used for all sorts of irrigation needs for the building. And this is a picture of the final project. You can see the carved facade that relates to the functions going on behind it, but also provides light and shading into the space. And this is the last one. So I've just got 3 more slides. This was a challenge. This is a competition. The challenge was, it was a building in California, and the idea was, the competition was called Small Hospital, Big Idea. So we entered this competition, and the thing that was fundamental that I just wanted to put on this slide was that the location they gave us for this competition was Lancaster in California. This is the amount of solar radiation, and the only one that's bigger than that is the Mojave Desert. So basically the natural resources we had on the site was sun. So the whole thing was about how do you do with sun. So anyway, I won't go into the detail, but basically came up with a strategy, which is represented by this diagram, which meant that all of the energy required for that running of that hospital for a year could be derived from this PV array. Not necessarily all at once, but over the course of the year. And so the project looked like this. So it's basically a whole series of buildings overlaid by a solar canopy, which was sufficient to collect enough energy for the whole hospital. We won the competition, but they didn't build it. So, and that was it really, just to say thank you, and hopefully that's just a little idea of 1 or 2 projects where we were able to show integration, collaboration, intuition, and research to back it up. Thank you.